Today we explore the cut method, an elegant trick for finding the stationary distribution of a Markov chain. Picture a series of rooms connected by doorways with people walking randomly through them. After a long time, the number of people in each room stabilizes, not because anyone stops moving, but because the rate entering each room equals the rate leaving. And the cut method exploits this balance. Draw an imaginary line across the system and demand that flow left to right equals flow right to left. Let us first define what we are after. The stationary probability, P sub k, is the long-run probability of finding the chain in state k. Equivalently, it is the fraction of time the system spends in state k. Next, how much flow travels along a single arc? Consider state 0 with an arc of intensity lambda 0, 1 leading to state 1. The mean number of jumps per unit time along that arc equals the intensity times the probability of being in the source state. The reasoning is simple. You can only traverse the arc while sitting in state 0, and once there you traverse at rate lambda 0, 1. Now consider a birth-death chain, where transitions only occur between neighboring states. Draw a vertical line, a cut, splitting the chain into two halves. In steady state, the total flow crossing this cut to the right must equal the flow crossing to the left. Only one forward and one backward arc cross. This gives the beautiful local balance equation, lambda k pk equals mu k plus 1 pk plus 1. Each cut produces one equation linking two neighboring probabilities. Chaining cuts gives us every pk in terms of p0. Let us put this to work. We have arrival rate 4, service rate 8 per server, 2 servers, and states 0 through 3. Forward arcs all carry intensity 4. Backward arcs are 8 from state 1, but 16 elsewhere because 2 busy servers serve at combined rate 2 mu. Cut between 0 and 1. Forward flow 4p0 equals backward flow 8p1, so p1 is 1/2 p0. The cut between 1 and 2 gives 4p1 equals 16p2, so p2 is 1/8 of p0. And the final cut yields p3 equals 1/32 p0. Now we normalize. The probabilities must sum to 1. Substituting back, we obtain the complete stationary distribution, 32, 16, 4, and 1, all over 53. Visually, most of the probability mass sits at the lower states. The system is usually nearly empty. Beware, the simple form lambda kpk equals mu k plus 1 pk plus 1 relies on the chain being birth-death. If arcs can skip states, sum every arc crossing the cut. And remember, pk is the fraction of time the system contains k customers, not what an arriving customer observes, except under Poisson arrivals where the pasta property bridges the two. To summarize, draw the chain, place cuts, write the balance equations, solve recursively, and finally normalize. With this elegant recipe, the stationary distribution falls into our hands.